Yes, good day. Today we are looking at once again this topic that we covered last time, quantum mechanics, quantum physics. Um, we looking at the question from 2021, October, November, paper 4, variant 1, question 10. I have question 10C. Yeah, we part 1 and 2, which we are going to address here. And um, the question, the 10A, let's start right from the beginning. Yeah, these two that are put on the board there, we are going to discuss them shortly. The first question was, state the experimental phenomenon that explains the, the particulate nature of electromagnetic waves. Right? Anyone? Good. It is the photoelectric effect, right? Because the we can only explain the emission of electrons from the surface of metal when we consider that electromagnetic waves are made up of the packets of energy with discrete amounts of energy. These packets are called photons, right? So it is the only way that can explain the photoelectric effect. The wave nature of light cannot explain the photoelectric effect. So the phenomenon that explains the particulate nature of light is the photoelectric effect. And the other question was the phenomenon that explains the wave nature of matter, not the wave nature of light, the wave nature of matter. Right. Anyone? This one, it is the electron diffraction. Remember, we discussed the Broglie experiment in which he accelerated electrons, and then the electrons had to pass through thin graphite. Remember, graphite is carbon, and then because the carbon atoms are structured in a way creating spaces, the gaps between the atoms, the electrons were passing through those narrow gaps, and there was diffraction. Not only diffraction, there was diffraction and interference, right? Right. So from that experiment, we broadly concluded that the particles that are moving, that have momentum, behave like waves, have wave-like properties. So the phenomenon that explains the wave nature of matter is electron diffraction, right? Right. And remember, we are dealing with small subatomic particles, right? When we are dealing with this, was when particles becomes bigger than protons, it becomes very difficult to detect the wave nature of moving particles. Good. Now, the next question was, says B, a particle that moves with momentum P, state the equation that gives the effective wavelength lambda of a particle, right? State the name and any other symbols used. Okay, so the equation is this one. It is lambda, right? Clear? Is Planck's constant divided by the momentum of the particle. This is the Broglie equation, right? So it's lambda equals Planck's constant. So name the variable there, Planck's constant. This is the momentum of the particle. And this one, we call it the effective wavelength. Or sometimes they ask you, what name is given to this wavelength? If they ask that question, I think it was in this question or some other question, I can't remember. It is called the de Broglie wavelength. What is the name of the wavelength? It is the de Broglie wavelength. Okay, this is the Broglie wavelength or the effective wavelength. And then you can replace this P with the MV. Momentum is mass times velocity. The mass being the mass of the electron and the velocity of the electrons. Okay, good. Let me take that one off. And then the next question is this one. It says electrons are accelerated from rest through a potential difference of 4.8 kilovolts, right? Right? Then show that the final speed of the electrons is 4.1 times 10 to the power 7. How should we address that? Can I do it right in the top there? Maybe. I think it's quite visible there because I don't want this thing, I want this thing to come clear. So let's start from work done to move electrons, because then we can apply the principle of conservation of energy. So the work done from our electricity work or energy is QV, right? So if you are given now our voltage is our V, our Q, the work done on the electrons and the charge is E, so it's going to be EV. So this is the formula that you will use to calculate the work, right? So that we can relate that work and change it to kinetic energy. So EV, so how many EVs if the voltage is 4,000, is 4.8 and 10 to the power 3, which is 4800. So it's going to be 4800 EVs, right? Okay. So these are the electron volts, right? Right. If the voltage is 1 volt times that, it will give you 1 electron volt. So 4,800 electron volts is the kinetic energy. So you can say half V squared is equals to 4,800 electron volts. To change electron volts to joules, remember we multiply by 1.6 times 10 to the power is negative 90. Right. Then you can make V, the sum of the formula is equals to square root of 2 times 4,800 times 1.6 times 10 to the power negative 19, right? Divided by the mass of the electron. Right. If you do that, 9.11 times 10 to the power negative 31 kgs. Do that, you find you get to that answer. 4.11 times 10 to the power 7 meters per second. Right, and then the last question says, calculate the effective wavelength lambda of a beam of electrons moving at this speed, right? So effective wavelength, we are going to use this formula, which is lambda is equals to P, we have to H, sorry, Planck's constant divided by momentum, which is mass times velocity. So the velocity, the mass of an electron, we know, H we know, so we can calculate the wavelength of the electrons. Which I think then you get an answer like 1.8 times 10 to the power minus 11. Try it, put H Planck's constant there, 6.63. 6.63 times 10 to the power negative 34 joule seconds divided by the mass of an electron, that number times the velocity of the electrons. You'll find the answer to be 1.8 times 10 to the power 11 meters per second. The beauty of the Broglie equation is that, for example, if you compare using X-ray compared to using electrons, you'll find that with electrons, you can manipulate, you can change the potential difference, and therefore you can manipulate your wavelength. You want your wavelength to match the space, the width, or the space between the gap. Yeah. The space between the atoms, for example, if you are studying crystallography, so you want the gap to be of almost the same width as the wavelength of the light. Whereas with X-rays, it's not easy to manipulate the wavelength, because they have a specific frequency and they have a specific wavelength. So you cannot change that. You cannot vary the wavelength of your X-rays. And also the other thing with X-rays is that if the material is thin and you're passing it through thin material, X-rays are very penetrating and they can end up damaging the material. So these days it's a lot easier that people have discovered that the wave nature of these small particles like electrons that you can actually use them to get the diffraction patterns, and if you are doing certain crystallography, you can use that to determine the structure of the elements or the atomic structure of different elements. So thank you. We'll meet again. I think this is it.